Okay, so this is part 3. We're going to jump ahead a little bit in the book to page 422, establishing infections. And a lot of this is going to be familiar from what we looked at in terms of viruses. There's a lot of similarities between how a virus gets into your cells and steals resources and makes copies of itself, to how a bacteria gets into your body, steals your resources, and makes copies of itself. Both of those processes start with adherence. So viruses had to stick to cells. Bacteria, they have to stick to cells too. Many bacteria are then outside of cells. They're in the body. They need to grow. They need to colonize the body, because they need to grow to those numbers that could then launch their attack. We'll look at how bacteria invade the body, and we'll look at how bacteria can manipulate our cells. So, slide 15. To cause disease, a pathogen must be able to establish an infection. Some microbes have to invade the body. Some microbes do, in fact, get inside our cells. They are intracellular parasites. Once they get inside the body, they have to survive. And we have all of the components of our immune system working against them. And we'll look at some mechanisms by which microbes can survive. Then, once the infection has established, the pathogen wants to get out of one host into another host. So just like viruses, they get into the cell, make more of themselves, get out, infect more cells. Bacteria, on a more kind of organism level, they get into one human, they colonize, make more of themselves, and then they want to get out of that human into a new human, and maybe into more than one human. And then they will make more bacteria, and they'll spread to more humans, and they'll make more bacteria. So it's about getting in, making more of yourself, and moving on. Many of the symptoms that we experience in relation to diseases is all about the bacteria getting out of the body. If a bacteria causes an infection that makes you cough or sneeze, or a virus causes a sneeze, that is a mechanism by which the pathogen is expelled from the body. If a bacteria gets in and releases toxins in your digestive system that give you diarrhea, that's one reason why, is because diarrhea is a very expedient method for an intestinal pathogen to escape the body and spread to the next host. Obviously, the immune response is vital and central to our ability to not only survive and fight back, but also our immune response can be manipulated by the microbe to hasten or make its transition from person to person easier. Okay, so on to slide 16. Adherence. The first thing a bacteria has to do before it can cause any kind of illness is it has to stick to your cells. So we have bacteria wanting to stick to cells, and the mechanism of bacterial protrusions that stick to host cell receptors, very similar to our viral spikes sticking into, say, a glycoprotein. In this case, a bacteria can have a number of different mechanisms for attaching to a cell. One of the most common mechanisms, these mechanisms are known as adhesins. Adhesin is the molecule that sticks into the host cell receptor. But one important mechanism that bacteria have, and the adhesins are then at the tips, are these little protrusions called pili. So you can see quite clearly here, here is the host cell membrane with its lipid bilayer. Here are the receptors. In this case, they may also be glycoproteins, like we saw in viruses. Sorry, they may be glycolipids, which are lipids and sugars. Molecules that are embedded in the membrane. And once again, these molecules do not want to be used by bacteria as receptors. They have an important function for the cell, just going about its day-to-day business. The bacteria here is exploiting these receptors. And just like viruses, then where a bacteria is going to stick depends on which adhesins it has for which receptors. And different tissues in your body have a different set of receptors. So a respiratory bacteria is going to stick to respiratory surfaces because those respiratory surfaces have the right receptors. If a respiratory bacteria were to get into your digestive tract, unlikely then it would be able to stick because the cells of the digestive tract would not have the right receptors, and vice versa. So there's a high level of specificity in the binding of bacteria to host cell receptors. The ability to adhere is an important virulence factor. Once a bacteria has got in, once it's stuck, it then needs to grow, colonize. It needs to grow to sufficient numbers. Many of our bacteria, as we looked at a little while ago, grow in these complex structures called biofilms. And all of the things we talked about in terms of biofilms, all of those interactions, the waste of one bacteria becomes the food for another. The idea that biofilms can be difficult or make it more difficult to control the bacteria. Biofilms are typically the bacteria extrudes some kind of material. Often that material is very sticky, and the biofilm then allows the bacteria to stick itself into your body. So you may cough up blobs of green-looking gunk, but you haven't coughed up the entire biofilm. The biofilm is still in there, and it can just regrow. Your dental plaque, the stuff you brush off every night and every morning, that's an important biofilm. A lot of different bacteria all working together in those microbe cities. So once the bacteria gets in, it has to survive and defend itself against all of our defense systems. And our first line defenses are all those antimicrobial chemicals that we produce. If you cast your mind back, you may remember this chemical called lactoferrin. and the ferrin part tells you that it's dealing with iron. Lactoferrin locks up iron and doesn't allow the microbe access. So the microbe fights back with molecules called siderophores. Siderophores bind the iron for use by the pathogen. So we have this battle over iron, the host trying to prevent the microbe from getting it, the microbe producing siderophores to try and extract that iron, use it for its own purposes. Iron, although we only need it in very small amounts, and indeed all organisms need it because it is central to many essential biochemical pathways. Let's imagine a bacteria has gotten into our body, into our digestive tract, or into our respiratory tract, or maybe into our urogenital tract. It's going to come into contact with mucous membranes, and one of the most significant defenses that mucous membranes have is secretory IgA, and that's this picture up here. That's that Ig, antibody that has the two Y's stuck together. Secretory IgA, also present in saliva and tears and breast milk, as a kind of another one of those first line defenses. So let's just quickly recall the structure of antibodies. They have this Y-like shape, and at the tips here of Y we have our variable regions, and the variable region of our antibody can change its shape, and this is where it'll bind to the antigen. So this is the antigen binding site. So our antigen binding site is looking for a particular shape of molecule. Our bacteria has that molecule on its surface. That allows the antibody to stick to, in this case, the bacterial surface. And then sticking of antibodies to antigens can trigger a number of different events. Pili are a good target for bacteria. We may cover a bacteria sticking IgA to its pili. So one way, again, there's typically this arms race. If our bacteria can simply shed its pili, so here's our bacteria. Here's our bacteria covered in pili. Here's our antibody stuck to all those pili. Pili turnover and pili shedding means that the bacteria can just shed its pili, and all of the antigen that was sticking to it is now no longer sticking to it. Very similar mechanism in the idea behind humans shedding their skin. Not all at once like a snake, but our cells are constantly being lost. They die, so the very surface of our skin is dead cells, and then pieces flake off, and the idea is that a piece of skin, bacteria have landed on the skin. They're trying to grow, so we allow the removal of microbes by just releasing or shedding our skin. Bacteria shedding their pili has a similar outcome. Antigenic variations. So those proteins on the pili or the proteins on the bacteria, the proteins to which our antibodies are made. So there's a particular protein and it has a particular shape, and that particular shape can be recognized by the antigen binding site of a particular antibody. So the bacteria has variations of this protein inside its genome, and it can switch on and switch off various variations. So the next time the bacteria makes this structure and this protein, it has a different shape. And now our antibody that could once bind and recognize no longer has a shape match and can no longer stick. If it no longer sticks, it can no longer identify this particle as being a particle for the immune system to fight against. Another mechanism is that we have bacteria here. We have our IgA. Our IgA is on its way. It's going to stick. It's going to identify this bacteria as being a danger, and then the immune system is going to take care of that danger in some way. So the bacteria releases a digestive enzyme, and that digestive enzyme snips up the IgA before it can ever reach the bacteria, in which case, again, the IgA and the antibody can't tag the bacteria. So pili turnover, antigenic variation, IgA proteases. Proteases are enzymes that break apart proteins. In addition to that, they have to compete with our normal microbiota. So in one of the major ways that our normal microbiota help us is just by taking up space in or on our bodies. And they can be very competitive. They want to live in that spot in your lung, or they want to live in that spot in your intestines, and they're not going to be willing to give it up. So they will compete and they'll fight, often using toxins against each other. If there's no space, then the pathogen can't stick. This is what we mentioned in terms of antibiotics. Broad spectrum antibiotics can often have long-term nasty side effects because they disrupt the normal microbiota, they kill them off. That leaves these kind of blank spaces on our surfaces, and it's those blank spaces that are kind of prime real estate for many pathogens, particularly opportunistic pathogens. Let's do that one here, and we'll carry on with this section in a second.